This is Unit 12 for the AP Physics C exam review. We're going to look at magnetism, and we've all heard of magnets, right? And they exert magnetic fields on one another that cause them to get attracted. But in order to understand that, you have to understand how magnetic forces work at the most fundamental level when you look at charged particles, right? So let's say you have a charged particle, positive Q. And if it's going through some sort of magnetic field, right? And I'll kind of draw it like so with these vector lines, because magnetic field, we use the letter B. It's akin to electric field, but we know that the electric force, right, would just equal that charge Q times E, right? Regardless of if you just place a charge in an electric field, it'll experience this force. But in a magnetic field, this charge might not actually experience any force. In fact, it'll only experience a force once it starts moving with the velocity v. And not only does it have to be moving, it can't be moving parallel to the magnetic field. If the charge was moving like if you had a separate charge, positive Q with big Q, if it was moving along with the magnetic field, it would actually experience no force. That's pretty odd. And the other odd thing is, well, if you have a charge going through a magnetic field, it won't deflect like this. It will deflect like this. Like it'll go out of the page, which is weird. That's really weird. I thought electric fields, they represent the direction of the force, right? It represents the direction that a positive charge would accelerate, but with magnetic fields, that's not the case. So the equation for magnetic fields, the equation for the magnetic force is Q times V cross B. A cross product, like torque, right? So force, it's a vector, and it's going to be Q times the cross of the velocity vector and the magnetic field vector. So the magnitude of magnetic force, right, if you think about the magnitude of a cross product, it's just going to be Q, V, B sine theta, the angle in between them. So, if theta is 0, right, if the charge is moving parallel to the magnetic field, you won't get any force. If V is 0, you get no force. And, obviously if the charge and magnetic field are 0, you also won't get any force. So this gives us the quantity, but remember, force is a vector, it has direction, and it's going to have the direction of the cross product between V cross B. Now, how do you find that direction? Well, there's something called the right-hand rule. Now, I'm assuming you're taking this class and your teacher has taught you a right-hand rule, or maybe two right-hand rules, and one of them is for like forces. I would use that right-hand rule, right? Use whatever right-hand rule your teacher taught you. I learned it as your V is this way, your B is your middle finger, and then your resultant vector, your force, is the thumb. I know people who have like V, B, and then your palm pushing in the direction of the force. There's a lot of right-hand rules for like cross product. Use the one you're comfortable with, right? But it all works the same. Look, V, B, my force is going to be out of the page. So get comfortable with the right-hand rule. If you have a you could have magnetic field that's coming out of the page, right? So this is a magnetic field coming out of the page. It looks like dots, like if you think about an arrow, right? And then this would be magnetic field going into the page, right? It looks like the tail of an arrow, right? Sticking into the page. So if I have a charge here with speed v, it's going to be v, b, the force is going to point down. Same thing here. If I have a V, the magnetic field is now into the page, so the force is going to point up. This flips with negative charge, right? In the same way that negative charge kind of has opposite, it it has the magnetic or the electric force, right? It's opposite in the direction of the electric field. Kind of similar to that, negatively charged particles have opposite forces, right? So if this was a negative charge, negative Q, you would do VB, which would seem to have a force pointing down, but then you flip it, so it's a force pointing up. So just remember that conceptually, right? Negatives, positives, they're opposites of one another. A cool application of the magnetic force would be something called a mass spectrometer. So mass spectrometers are used to determine the mass of any particle you want, right? Anything that's, you can't really measure the mass of, but has a charge, you can actually use it to figure out the mass. Here's how it works. If you have, let's say you have two plates, one of the plates has a, has a charge. So if let's say I want to find the mass of deuterium, right? Like a deuterium nucleus, which has, I think, two protons, 2 neutrons. Well, if this is a positively charged plate and this is a negatively charged plate, this deuterium atom is going to go through a potential difference, and it's going to build some sort of speed. So, the exact speed, you can use conservation of energy, right? It's going to go through a potential difference V, and I know the charge, so the change in UE is going to equal Q times change in V, and that change in UE is directly going into the change in kinetic energy, which starts at rest. So it's going to have a final kinetic energy of 1/2 mv squared, and then I can solve for V. So I get V is going to equal 2Q times change in V over M, and you take the square root, right? So boom, I have that would be the velocity. Now let's say I don't really know the potential difference, or like maybe I'm adding deuterium and I'm not going to get exactly the velocity that I kind of want. So what I can also do is have it go through what we call a velocity selector. So if you have two plates like so. This is a positively charged, thing going through with the speed v. And let's say the top plate is positive. Well, we know that this positively charged particle is going to deflect down, right? It's going to go get attracted towards the negatively charged plates, and also the electric field points down. So we need to have actually a magnetic field to kind of balance that out. So which way should the magnetic field be? Well, my speed is going this way. I want a force pointing up. So you could see the magnetic field would have to point into the page, right? So I could see that, well, FB balances out FE. So in that case, well, FB is just QVB, right? No sine theta because the magnetic field and the velocity are perpendicular, right? VB, right? Force is just perfectly, there's no angles between them, or there is an angle, it's 90 degrees. I don't know what I'm saying. QVB is equal to Q times E. So I can see Q's drop, and I get V is equal to E over B. So this ratio, right, if I know the electric field that I have going on, which, is just the voltage divided by distance. If I know the electric field, take that over the magnetic field, that actually gives me the speed at which this particle is moving in order to not deflect, right? Because if it's moving faster than this, right, if V is bigger, well, think about it like this. If you're moving faster, there would be a bigger magnetic force, so you would deflect up. If you're moving slower, there's a smaller magnetic force, so you would deflect down because the electric force takes over. So this speed, I know that any particles that make it out of here without deflection have this speed v. And that's how I can determine the speed. And then it would then enter maybe some sort of magnetic field pointing into the page, right? And it would actually then start going into uniform circular motion with a radius like r, right? So if I know if it deflects a distance d away, the radius would be d over 2. Ideally, I think. Technically not. Actually, yeah, it would have to be d over 2, I think. unless it kind of hits like that. Oh, let's just say it makes a semicircle. The radius would be d over 2. And then I can use, well, and why, first of all, why is it going through uniform circular motion? Well, the speed is v, so I know v and the b would create a force pointing up, which would change its direction, right, because the force is perpendicular to the v. But now at this point, the v is this way, so VB would cause a magnetic field pointing in, and because it's always perpendicular, the force is always perpendicular to V and B, it would end up being a centripetal force that'll always be perpendicular to the velocity, uniform circular motion. So I know that the net force would equal mv squared over r, and then, net force is just the magnetic force QVB. If I know the magnetic field, I can solve for m, and one of the v's drop, right? Because it's v on this side, v on the other. So QB over v, or QVR over v, that's the derived equation for mass. So I can, if I know the radius, I can actually figure out what the mass would be. Whew! Okay, so that's just magnetic forces in a nutshell. Hopefully I talked about everything. Yeah, I think I did cover what I wanted to cover. Right-hand rule, all that fun stuff. Oh, I guess, yeah, I should say this. Sometimes you could have current. What is current? Current is just moving charge. So you can derive this equation, but the magnetic force on a line of current would actually be equal to I and then L cross B, where L is the direction of the wire. I don't know why. Yeah, it's like the direction of the current is really going, the wire, right? So yeah, it's the direction of the current specifically is going, because current is really a scalar, but that length vector tells us that. And yeah, this just comes from, Q is really equal to I dt, right? Like dq over dt is equal to I. So I dt times v, right? V times dt would end up being distance. So you get ILB. Now let's talk about magnetic fields, because it's cool. These particles can experience magnetic forces, but how are magnetic fields created? Well, believe it or not, they're actually created from moving charge. It's pretty crazy. The magnetic field due to a point charge ends up being mu naught. I'll explain this equation a bit further, but mu naught, that's a constant. It's actually equal to 4 pi times 10 to the negative 7th. So why are we doing mu naught over 4 pi? I don't know. But the magnetic field due to a charge will equal Q, and then we have our V cross R hat over R squared. So if I know a charge, Q, that is, at a certain distance R away, then I would take this distance R, square it, and then I could figure it out. But this V cross times R hat is actually the unit length, or the unit vector that points in the same direction as R. So V cross R just helps us figure out the direction, because this R hat tells us that we're taking it cross in the direction, right? You could do V cross just R, but then you're dividing by R to the cube, right? So this is how we do it. So the magnitude of B, right? Magnitude of B will equal mu naught over 4 pi times QV sine theta over R squared, where sine theta is the angle between V and R. So how do magnets work, right? Like, we're talking about charges that are creating and reacting to forces. Well, magnets aren't really charged. How do they work? Well, the deal with like permanent magnets is that the deal with permanent magnets is that if you have a permanent magnet, I don't know why I drew it like a cylinder, but permanent magnets, they're made up of atoms, and in a very simplified case, the atoms their electrons, they're essentially spinning, right? Once again, not really true, but for the purposes of this class, we can simplify it like that. And what happens in a magnet is that all of the atoms are aligned so that so that the electrons are spinning in the same direction. And you can kind of think about right-hand rule, right? If you have an electron spinning like so, right-hand rule tells us that that magnetic field, right, will actually point upwards. So, right, when I do V cross R hat, right, because R hat, I should show it like this. V R hat, the magnetic field would point out of the page, or in this case, up. So when they're all aligned, we actually call them magnetic domains. When all of the magnetic domains are aligned upwards, you get a net magnetic field, right? If I get all the domains pointed upwards, I get a net magnetic field, because they're all producing small magnetic fields. The net effect would be a total magnetic field like so. And yes, the magnetic field does indeed go through the actual magnet, right? Because the magnetic fields in here, right? They're in the magnet too, right? The domains and stuff. So we call them magnetic domains. When objects aren't magnetized, their domains are not all aligned. So instead, they would have domains like so, which essentially cancel each other out, all those magnetic fields, and you get no more net magnetic field. That's how those work. And the magnetic field lines that I kind of drew here, they tell us the direction that a north pole of a magnet would point to, right? So magnets exist in two poles, never one, right? They always have a north and south. Even if you split it in half, it'll end up creating a north and a south, right? If I split it right here, it'll actually create, if I split it right here, there would end up being a south and a north here when I split it. But north and south, right, these lines tell us the direction that a north pole magnet would kind of point towards, right? And hey, that's what compasses are. The red needle of a compass is really just the north pole of a magnet. It's a magnetized needle. So, on our Earth, the north pole, right, is actually the south pole of a magnet, because our needle, right, the spinning iron in our core generates a magnetic field, and similar to the domains, kind of, right, the motion. So this would point upwards, so that if this was the actual north pole, my magnet would align in the direction of that magnetic field. It would adhere away from the north pole, the magnetic north pole, which is really the south pole. So that's how we kind of represent magnetic fields. It's kind of cool. And for a wire, right? For a wire, let's say I have a wire of current, like so. I can use my right-hand rule and be like, okay, at this point, right above it, the magnetic field created would kind of point to the left, and then to the left, and then the magnetic field at a point to the left would be I cross B, kind of pointed downwards. And essentially what I'm getting at is you get a circle. You get a circle where the magnetic field is always tangent to the circle. So the magnetic field swoops around the wire. And what is the magnetic field due to a current? Well, this is actually Biot-Savart law. And this is really Biot-Savart law. But Biot-Savart law, in its most beautiful form, tells us that the magnetic field due to a wire, well, the small magnetic field due to a small portion of the wire is mu naught 4 pi I dl cross r hat over r squared. And if I integrate that, I get that the total magnetic field is equal to mu naught over 4 pi integral I dl cross r hat over r squared, right? If you actually compute this integral for a very long wire, right? For a very long current-carrying wire, you would use bounds -infinity to infinity somewhere in the process. If you want, I'll derive it one day. But you essentially get B is equal to mu naught I over 2 pi r. This is the magnetic field due to a wire. So at a distance r away, it produces a magnetic field according to this this equation. I don't know why I decided there. So yeah, I think kind of what I wanted to talk about for that. Kind of example Biot-Savart law in a more different sense. Let's say we had a weird section of wire or current carrying loop, kind of made like a rainbow looking thing. So this is all just wire that loops around, and I have a current I going through it. I want to find, well, what's the magnetic field at the center? The center C. If this is a radius R1, again, these are semicircles, and this is a radius R2. Well, I would use Biot-Savart law in this sense, right? Because I want to integrate over the small lengths of the wire. I would integrate to find the total. So here's the deal, though, right? What makes this kind of nice is that, well, the current, if I draw out the current, it would be looking like this and this section and then looping around like so. Well, the nice thing is that, these straight portions of wire, because they're, collinear, I guess, with the center, right? When I take the cross product, right, the current is parallel to the direction of the distance, right? So that would actually have zero magnetic field contribution because, if I change this, if this is sine theta, right? So B is going to equal mu naught over 4 pi times the integral I dl sine theta. In these cases, theta is 0. So the whole integral turns to 0. Now, thanks to these arcs of wire, though, that are circular, the theta between, because this is like the center of the circle, it's always going to be theta 90 degrees, right? They're always, the radius is always, perpendicular to the tangent of the circle. So it's always going to be sine theta, or 90 is equal to theta, so I don't have to worry about the sine theta. Sine 90 is always going to be 1. So I dl over r squared, well, for one section of this, right, if I think about right-hand rule, I should mention the second right-hand rule. Second right-hand rule tells us that, you could do this right-hand rule to find out, you could use this right-hand rule to find out the direction, but an easier right-hand rule for stuff like swirling magnetic fields would actually be point your thumb in the direction of the eye, and then your finger kind of tells you, the direction. So if I integrate this for one section of the wire, if I use the first right-hand rule, I can see it's always going to be into the page here, right? If I do IR for all these sections, it's always going to be into the page. Otherwise, for here, it's always going to be out of the page. So the net magnetic field is going to be this integral for the first loop, right? Minus this integral for the second arc of loop. For the first arc of loop, the current in the radius is actually just constant, right? So it's going to be mu naught times I over 4 pi r1 squared. But now the dl, if I integrate dl, that's just the length, which is just half the circumference. That's just pi r, pi r, right? Pi r1. So the pi's drop, and then one of the r's drop too. So it's the same thing for r2, right? But now it's going to be mu naught times I over 4 pi r, or 4r2 squared, right? Or not squared, it's just going to be r, because one of the r's drop. So you could see that the overall magnetic field will be into the page because this component, the R1 component, is stronger because it has a smaller radius. So it's going to point into the net magnetic field will point into the page. So that's just an example of Biot-Savart law. Main idea also, just in these derivations, right? The straight part of a wire that's collinear with the center, it won't have any contribution. So now, Biot-Savart law for some nasty stuff, if you try to derive the magnetic field due to a long current carrying wire, it's kind of hard, right? It's a hard integral. But Ampere's law helps simplify things. So Ampere's law is kind of like Gauss's law-ish. Now Gauss's law for magnetism, by the way, if you do the magnetic flux enclosed by a magnet, it's always going to equal 0. And this is the idea that you will never have just a north pole or just a south pole. Whatever magnetic field comes out of the north pole comes back into a south pole. So that flux, right, whatever's leaving my flux will always, whatever's leaving that Gaussian surface will always come back in. The net flux will be 0. But Ampere's law tells us that the line integral of the magnetic field through space, right, B dot ds, will actually equal mu naught times I enclosed. So to kind of help you visualize, this is kind of hard to understand. Let's say you had wire coming into a page, wire coming out of a page, wire coming into a page, wire coming out, wire coming in, I don't know, whatever, right? A bunch of wire coming in and out. Well, if you were to draw some sort of loop, I'll make this loop a bit thicker, but if you were to draw some sort of loop around certain wires, right? These wires are all creating all sorts of magnetic fields along this line, right? Because, you know, you could use right-hand rule to figure out, you know, the magnetic field at this point, magnetic field, whatever, right? Or it should be into the page. But if you were to integrate the total magnetic field along this loop, no matter how crazy the loop is, or no matter how, you know, how many wires there are or whatever, that line integral will always evaluate to mu naught times the enclosed I. So if this is 2 amps, right, for example, it would be 4 amps times mu naught, which is, by the way, the magnetic, I always forget, it's either permittivity or permeability, I always forget. But it's a constant, and yeah, like, you know, these are not enclosed within the loop, so they have no contribution, right? Because if you think about it, if you're going along this path, right here, it's like the magnetic field is like kind of helping your path, right? When you take the dot product, the length and the magnetic field are in the same direction, but then it's also in the same direction here, but now you're looping the other way. So things outside the loop have no contribution. This is helpful in the same sense that Gauss's law for electrostatics is helpful. It helps us exploit some symmetries, right? Because if you have, let's say you have wire, right, coming into a page with a current I can use symmetry. I know it's going to be circular, right? Or I know like the magnetic field is circular around a piece of wire, right? Equidistant points from the wire will have the same magnetic field. I can use this integral to find the magnetic field along any point on the circle, right? Because if it's a point r away, you could, by symmetry, you could pull b out of the integral. So b integral ds then equal mu naught times I enclosed. I don't know if this is proper notation. Calc 3 students, I'm sorry. But b times 2 pi r, right? That's the total length, like the circumference, the total length of that loop, that Amperian loop, similar to a Gaussian surface. And I get my equation, right? B thinks a wire is mu naught times I, which is the current enclosed by the loop, over 2 pi r. So yeah, that's Ampere's law. You can do some other crazier examples. I was gonna do an example, but I don't want this video to get too long. You could practice Ampere's law with a lot of things, but one last example would be a solenoid, right? Let's say you have wire, like so, right? A loop of wire, right? Which way would the magnetic field point? Well, if you have current going this way, you can imagine, you know, if you think about your right-hand rule, there's going to be current, you know, it's going to be basically magnetic field pointing this way, right? Because all the I at this point, right? Any I that's swooping up, you know, the I over here would create magnetic field pointing into the loop, and then the magnetic field here, or sorry, what am I saying? the current here would create magnetic field pointing right inside the loop, and then current over here on the outer part of the loop would have magnetic field in the same direction. Kind of hard to visualize. There's going to be an overall magnetic field going through the loop. This is actually how you can magnetize iron, right? You can't magnetize this because the domains, it's probably a chemistry thing, but the domains are very much fixed in a place. But for something like iron or cobalt, or maybe cobalt, ferromagnetic materials, their domains can shift. So if I place a magnetic field, the domains would actually align with the magnetic field and would create, I can magnetize this so that it has its own magnetic field. But the magnetic field strength, to find it, I could use Ampere's law, right? I can make a loop that's like kind of rectangular-ish, like so. And I know that the magnetic field along this line, right, it would be constant. So the B magnetic field times integral ds would equal mu naught times I enclosed. Now, let's say the total length is L of this kind of coil or solenoid, and let's say there are n turns. Well, n turns means that there's current coming right out of the page, if you could imagine, right, coming out of the page, piercing through the loop n times. So it's going to be n times I. Well, this integral, right, the magnetic field, right, this integral would end up being L, right, because there's no magnetic field at this point, but there's magnetic field over here for that part of the loop. So you get BL is equal to mu naught times n times I, divide both sides by L, you get B equals mu naught times little n times I, where little n is a number of turns per unit length. So that's another example of Ampere's law. This has been magnetism. We will talk about electromagnetic induction in a future video, unit 13 specifically. But yeah, hopefully this was a good review.